Welcome to this explainer on the hidden engineering that literally powers our modern world. Today, we're diving into something that's, well, completely invisible to most of us, but absolutely crucial. The incredibly efficient process of separating solids from liquids. It's a monumental feat of engineering that keeps global industries humming, and we're going to explore exactly how it all comes together.
To kick things off, I want you to consider a seemingly simple question. How much energy does it actually take to separate the wet from the dry? Just imagine you've got this wet slurry of material, and you need to get it down to a completely dry powder. Your very first instinct? Probably just boil it, right? Use heat, evaporate the liquid away. But thermally drying things out is remarkably demanding on a planetary scale. Why? Because water holds on to a massive amount of latent heat. So what if, instead of boiling it, we simply push the water out mechanically?
Well, it turns out mechanical separation is actually more than 100 times more energy efficient than thermal drying. 100 times. That is a staggering difference. By using mechanical filtration to basically squeeze, spin, or drain as much liquid out of a mixture as possible before we ever even think about applying heat, engineers are saving an astronomical amount of energy. Establishing this huge energy differential really sets the stakes for us today, because optimizing mechanical solid-liquid separation is, for sure, one of the most critical challenges in industrial engineering.
So here's our roadmap for today's explainer. We'll start by exploring the world of filtration. Then look at building the cake, going deep with depth filters, compare crossflow versus dead-end systems, and finally wrap up with choosing the right tool. Let's jump right into Section 1, the world of filtration. The invisible ubiquity of separation.
When you look at this vast web of applications, you realize the scale of filtration is truly massive. Solid-liquid separation is literally the backbone of nearly every sector of human activity. Whether it's biotechnology needing pristine cell culture clarification, the food and beverage industry giving us clear fruit juices, or beneficiation in mining, or, just purifying the drinking water we rely on every single day, none of it is possible without this tech. Every one of these industries relies on manipulating particle size, liquid viscosity, and pressure to pull the wet away from the dry.
Moving on to Section 2, building the cake, using the problem as the solution.
Now, normally, you'd probably think that a buildup of particles on a filter is a bad thing, right? Like, it just clogs the whole system up. But cake filtration is this brilliant mechanical method where a thick layer of particles, which is actually called the cake, forms on a filter medium, and that layer literally becomes the filter itself. Engineers use the buildup to their advantage. The initial filter cloth really just catches those first few particles, bridging the gaps, and then the actual product does the rest of the heavy lifting. This setup allows for extremely precise particle washing and hits the absolute lowest mechanically possible moisture contents.
The whole cycle breaks down into these 5 steps. It begins with a feed, bringing the slurry in. Next up is cake formation, where pressure forces the liquid through and leaves the particles behind. Then we have washing, to flush out any soluble impurities still hiding in the moisture, followed immediately by deliquoring to squeeze out those very last drops. And finally, the discharge step removes the solid product completely from the machine.
When you watch this cycle play out, you can see the slurry enter the apparatus. Notice how those solid particles start forming a really dense bed at the bottom, while the clear filtrate just drains out right beneath it. Once that cake is fully formed, a fresh liquid is introduced from the top to wash it. And finally, the mechanical apparatus physically kicks out the solid cake, leaving an empty, clean chamber that's ready to start the whole shebang all over again.
All right, Section 3, going deep depth filters. The 3D obstacle course.
So if cake filtration is all about building a layer on the surface, depth filtration is about trapping particles inside a three-dimensional porous maze. It's basically a direct mimic of how the Earth naturally filters groundwater through deep layers of soil and rock. This is the exact method engineers turn to when they're dealing with highly diluted slurries that have tiny submicron particles. A standard surface filter would just get plugged instantly by these things, but a depth filter, it allows the liquid to flow straight through while those tiny particles get snagged deep inside this massive network of pores.
To really ground this concept in some real engineering numbers, take a look at these parameters comparing 2 common deep bed media, sand and anthracite, which is a type of hard coal. Check out the media depth here. We're talking about beds of material up to 215 centimeters deep. That is over 7 feet of solid media that the water has to navigate through. And with effective particle sizes sitting in the 2 to 4 millimeter range, you can achieve filtration rates of up to 24 meters per hour. These are massive, continuous systems that are heavily utilized in municipal water treatment.
Let's move to Section 4, crossflow versus dead end, the battle of flow direction.
When we're dealing with delicate membrane filtration, the ultimate enemy is fouling. That's when the membrane gets permanently clogged up. So let's compare two different approaches to handle this. Dead-end filtration is kind of like a vertical traffic jam. The liquid flows directly into the filter at a strict right angle. Now, you get great flow at first, but a thick cake quickly builds up, meaning the whole system has to be stopped and cleaned out. Cross-flow filtration, on the other hand, turns the fluid horizontally. The liquid flows tangentially, perfectly parallel to the membrane. It's essentially like a sweeping river that naturally flushes the cake away as it filters.
So why is cross-flow so incredibly prized in industrial processing? Well, because the fluid is constantly sweeping the surface clean, it naturally prevents that nasty membrane buildup. You don't even need to add extra chemical filtrates. Plus, the lifespan of these highly sensitive membranes is drastically improved, and most importantly, it prevents irreversible fouling. It's a total game changer because it allows a plant to run continuously with a nice constant flow rate instead of constantly stopping and starting like you have to with a dead-end system.
Finally, Section 5, choosing the right tool, scaling and combining systems.
When you map out the modern engineer's toolkit, it reveals something pretty fascinating. The physical properties of the slurry strictly dictate the machine you use. When you compare particle size against the required pressure, the choices become really clear. Say you have large 10mm chunks and you just need some basic hydrostatic pressure. A vibrating screen works perfectly fine. But as your particles get tiny, like down to the microscopic 1 micron level, you suddenly have to apply intense mechanical pressure. That forces you to select heavy-duty equipment, like a tubular diaphragm press filter. The physics of the slurry literally write the rules for the mechanics of the machine.
And honestly, the variety of these machines is just staggering. There are over 3,000 distinct particle separation apparatuses out there on the market today. 3,000. And engineers rarely rely on just one. They typically string them together, maybe pre-thickening a slurry in one machine before feeding it straight into a centrifuge to hit that perfect exact moisture content.
The source material actually summarizes this dynamic beautifully, stating, "This evolutionary process of mutation and selection exhibits some similarities to biological processes. Driven by the intense economic need for efficiency, engineers are constantly inventing new technical mutations. If a new centrifuge or filter press is more successful at saving energy or maybe outputting a drier product, it survives in the market. If it doesn't, it goes extinct. It is a wildly competitive industrial ecosystem."
Which brings us right to the frontier of this technology. We're currently moving toward intelligent filters. These are machines that can actually sense changing feed conditions and adjust themselves on the fly. The absolute holy grail right now is the digital twin, creating a perfect virtual simulation of these complex fluid dynamics and particle behaviors. Think about it. If we can run a multi-scale simulation in a matter of seconds, we can optimize raw energy consumption before a single drop of liquid ever enters the physical machine. So I'll leave you with this to ponder. As our software rapidly catching up to our hardware, how much farther can we push the very physical limits of separating the wet from the dry?